Welcome to WikiPodcast.
Hey everyone, and welcome to another deep dive. Today we're really getting into something fundamental in classical physics.
Circular motion.
Exactly. How things move in circles and, well, the forces that make it all work. Sort of exploring the path of forces, you could say. We've got some really interesting material to work through.
That's right. And our mission really is to pull out the core ideas from all this to give you a solid handle on circular motion, orbits, basically why things curve instead of just, shooting off in a straight line.
And you see it everywhere once you start thinking about it. I mean, the obvious ones, like satellites zipping around Earth, or maybe those intense roller coaster loops.
Definitely. But also smaller things.
Yeah, like the blades on a ceiling fan, or swinging a stone on a rope.
Even just your car turning a corner.
Right, or tiny stuff like an electron in a magnetic field, or gears inside a machine. It's all the same underlying physics.
And that physics really starts with Newton, his first law, basically.
Objects want to go straight, pretty much, yeah. Straight line, constant speed, unless some force interferes. So to get something to constantly turn, to follow a circle, well, there has to be a force involved.
A force pulling it off that straight path.
Constantly pulling it and always pulling it towards the center of the circle it's making.
Okay, and this inward pull, this force, it has a specific name, right?
It does. It's called the centripetal force. Kind of means center-seeking.
Centripetal, okay. So let's dig in. What exactly is circular motion fundamentally?
Well, at its core, it's just moving along the edge of a circle,
Mm-hmm.
or even just part of a circle, an arc.
Simple enough.
And the material notes it can be uniform, meaning the speed stays the same, or non-uniform, where the object speeds up or slows down while it's curving.
Okay, here's something that reading through this felt a bit weird at first. Even with uniform circular motion, constant speed, perfect circle. The sources say the object is constantly accelerating. How does that work? Constant speed, but accelerating.
Right. It seems contradictory, doesn't it? But it all clicks when you remember velocity isn't just speed.
It's speed and direction. It's a vector.
Exactly. So even if your speed is locked, say 30 miles per hour, if you're moving in a circle, your direction is changing every single instant. You're pointing north, then northeast, then east.
No, okay. The direction keeps shifting.
And any change in velocity, whether it's speed or direction, is acceleration. That's the definition. Think of an arrow showing the object's velocity, pointing tangent to the circle. As the object moves, that arrow just keeps turning, constantly pointing in a new direction.
So the acceleration isn't about getting faster, it's the constant turning, the redirection.
That's it, precisely. And for uniform circular motion, that acceleration vector, it always points directly towards the center of the circle. That's what we call centripetal acceleration.
Okay, centripetal acceleration, pointing inwards. So sticking with that uniform case, constant speed, constant radius. What force is actually causing that inward acceleration?
Well, that's where the centripetal force comes back in. Newton's second law, FML. If you have acceleration, you need a force in the same direction.
So the inward acceleration needs an inward force.
Exactly. The centripetal force causes the centripetal acceleration. And it's important to remember, this isn't some brand new type of force like gravity or electricity. It's the job that other forces are doing.
What do you mean the job?
Like, for a satellite, gravity is the centripetal force.
Yeah.
For the stone on a string, the tension in the string is the centripetal force. For a car turning, friction between the tires and road provides it. It's the net result of whatever real forces are pulling inwards.
Got it. And if that force suddenly disappears, like the string breaks on the swinging stone example?
Poof. No more inward force, no more inward acceleration. The object just follows Newton's first law, inertia takes over.
It flies off straight.
Flies off in a straight line, tangent to the circle, right at the point where the force vanished. That's the direction it wanted to go all along.
Okay. The sources also get into quantifying this, right? Putting some numbers and relationships together for uniform circular motion.
They do, yeah. There are a few key things. There's angular velocity, usually written as omega. That's how fast the angle is changing, basically the rate of rotation.
Okay, radians per second or something like that?
Right. And that relates directly to the actual speed, the linear speed, along the circular path. The relation is simple, v/r. Speed equals angular velocity times the radius.
Which makes sense. If something's spinning, points further out from the center have to travel faster to keep up, even if they rotate at the same rate, like the tip of a fan blade.
Exactly right. Then there's the centripetal acceleration itself, axis. Its magnitude depends on speed and radius. Axis equals v/r. Faster speed, tighter turn, bigger acceleration needed.
Or you can write it with angular velocity, too.
Yep, substitute v, and you get x, or gar, same thing. And finally, the force needed, the centripetal force, Fc, just FMA, so FCC and VR.
Which means FC equals mv.
That's the one. Force depends on mass, speed squared, and inversely on the radius. More mass, more speed, or a tighter turn all require more force.
The sources had a neat little example, didn't they? A 1 kilogram mass.
Yeah, simple numbers to illustrate. 1 kilogram object, 1 meter radius circle, rotating at 1 radian per second.
Okay, so omega is 1, r is 1.
Right, so its speed, GVR, is 1 times 1, which is 1 meter per second.
Okay.
Its centripetal acceleration, HCVRR, is 1 over 1, which is 1 meter per second squared, inwards.
And the force needed.
HCVVR is 1 kilogram times 1 Wettermort over 1. Just 1 Newton. It lines up nicely.
And looking at some of the real-world numbers the sources mentioned, wow, the amount of acceleration can vary hugely.
Oh, absolutely. It's a massive range. You take something like a lab centrifuge spinning really fast with a tiny radius. And you're talking about accelerations thousands of times Earth's gravity, thousands of Gs, as they say.
Thousands. Okay, and then like a roller coaster loop.
Still pretty intense. Maybe tens of Gs, especially at the bottom of a vertical loop. Makes you feel heavy.
But then just turning onto a highway on-ramp in your car.
Much, much less. Maybe only a fraction of a G. You feel it, but it's mild compared to the other examples.
And that G is just comparing the acceleration to Earth's gravity at the surface, right? Like a benchmark.
Exactly. 9.8 meter series. It just gives us a relatable scale for these accelerations.
Okay, so that covers the uniform case, constant speed. But what about non-uniform circular motion? When you're, say, speeding up or hitting the brakes while turning.
Okay, yeah. Now things get a bit more layered. Because your velocity vector is changing in 2 ways now.
How so?
Well, its direction is still changing because you're on a curve. But now its magnitude, the speed, is changing too.
Right, speeding up or slowing down.
So you actually have 2 components to the total acceleration acting on the object.
2 components, okay.
Yes. You still absolutely have the centripetal acceleration component, sometimes called radial acceleration. Its job is still purely to change the direction to keep you on the curve. Its magnitude is still calculated as VRR, using the instantaneous speed vice at that moment, and it still points towards the center.
Okay, so that part's the same, just using the speed right now. What's the other component?
That's the tangential acceleration.
Yeah.
Points along the path, tangent to the circle.
Okay. Like forward if you're speeding up, backward if you're braking.
Exactly. Its whole job is to change the speed, the magnitude of the velocity. Its size is just the rate of change of speed, dv dt.
So one component changes direction, the other changes speed.
Precisely. And the object's total, or net acceleration, is the vector sum of those two. It'll point inwards generally, but usually not straight at the center anymore because of that tangential part.
Okay, that makes sense. 2 jobs, 2 components. How do the forces work out in this non-uniform case then?
The key idea again comes from Newton's second law, but applied very specifically just in the radial direction towards the center. The net sum of all actual forces acting radially inward must always equal the required centripetal force, mva/r, needed for that instantaneous speed and radius.
So all the pushes and pulls pointing towards the center minus any pointing away have to add up to mvor.
Exactly. Whatever forces are actually there, tension, gravity, normal force, friction, their components along that radial line have to balance out to provide exactly mv/r.
Okay. The sources have this really interesting example. The person at the very top of a vertical roller coaster loop.
Ah, yes, that's a classic. And a bit mind-bending.
It said that at the very top, sometimes both gravity, your weight, and the force from the seat, the normal force, can be pointing down. How does that even work? Shouldn't you fall?
It feels totally wrong, doesn't it? But think about it. At the absolute top of the loop, gravity's pulling you down, yes.
Right.
Towards the center of the Earth,
Right.
and the track or the seat is above you. If it's pushing on you, it's pushing down on you.
Okay, both down.
And crucially, at the top of the loop, down is the direction towards the center of the circular loop. So both forces are potentially contributing to the inward centripetal force needed.
But why don't you fall out of your seat?
Inertia. Remember Newton's first law again. At that moment at the top, you have a forward velocity. Horizontally, your body wants to keep going straight.
Wants to fly off tangentially.
Exactly. So those downward forces, gravity plus maybe a push from the seat, are working together to provide the necessary centripetal force, mvIRR, to force your path to curve downwards, following the loop instead of going straight.
So the normal force from the seat isn't just reacting to your weight.
Not at all. The normal force is whatever value it needs to be, in this case pointing down, so that when added to gravity's downward pull, The total downward force perfectly equals the MVI required by your speed and the loop's radius at that instant.
Wow, okay. So if you're going really fast, the seat might have to push down quite hard to help gravity provide enough total inward force.
Precisely. And if you're going just the right minimum speed, gravity alone might provide exactly the needed MVR, and the normal force from the seat could momentarily be zero. You'd feel weightless.
That really clarifies it. The centripetal force isn't some extra thing, it's the net result of the real forces acting towards the center.
That's the key takeaway. It's the sum total inward force doing the job of turning.
This whole deep dive really shows how these maybe abstract physics ideas connect directly to things we see and feel. Satellites staying up there because gravity is doing the centripetal job.
Right, or the forces keeping you pinned in a roller coaster, or the friction letting your tires grip on a turn. It's all connected.
Understanding this is pretty crucial then for engineers designing rides or scientists tracking planets or even particles.
Absolutely. Predicting orbits, ensuring safety on the road or on a ride, analyzing complex systems. It all relies on understanding these forces and accelerations in circular motion.
Okay, so let's try to wrap this up. Key ideas. Moving in a circle always means changing direction, which means acceleration, centripetal acceleration pointing inward.
Even at constant speed.
Right, and that acceleration is caused by a net inward force, the centripetal force, which is provided by real forces like gravity, tension, or friction.
And if the speed also changes non-uniform motion, you get that extra tangential acceleration along the path, changing the speed, while the radial forces still have to add up to the required MVRR for the inward direction-changing part.
Got it.
So maybe next time you're in a car taking a turn a bit fast, or even just watching clothes tumble in a dryer, think about what's providing that inward force, what's actually making things turn instead of going straight. It's kind of cool to notice.
Thanks for listening. Write us your opinion in the comments, Alent. What is the most surprising everyday example of centripetal force you can think of? Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.